G'day viewers. In this segment we'll talk about network address translation, a networking technology that's widely used in the internet today. So many of you probably have a NAT or network address translation box that you use. This is because NAT boxes are commonly used to connect home networks to the internet, say as part of a wireless router or AP or any other kind of router device that connects your home network to the internet. We're going to cover them today and talk about what a NAT box actually is and how it does its job. And we'll do this for a couple of reasons. You might be interested just to find out how it works, since it's pretty much an everyday networking technology. That's one reason. And the other reason is it'll give you a chance just to think about how some of the NAT mechanisms fit with some of the principles of networking we've learned. Or rather, maybe you'll see how they don't fit and some of the tensions. Okay, so I'd like to start with just a little bit of a review of layering. You remember this layering model? This is the kind of slide we saw early on in the course. We have some applications using TCP at a source on the left, and there's a destination on the right. And that application is able to send information down the network. It goes across the network through routers and arrives on the other side. This is our standard layered model. The way layering worked with encapsulation, what it meant was that TCP passed information down to IP. It was encapsulated to be wrapped in a packet. That packet went through the network. I'll draw it at the router. So there was an IP packet on the outside, and on the inside was the TCP data, header and data. And because of our layering, this meant that IP devices didn't look at what was inside. They didn't inspect or modify the TCP packet in any way. This is a nice, clean layering abstraction. That's great in theory. That's actually the way a lot of networking devices work, but it's not the whole story. It turns out that there's a whole class of devices called middle boxes, of which NAT is going to be one example, of course. Now, middle boxes are these very odd kind of beasts which don't fit with our architecture at all. Middle boxes sit inside the network, so logically they're in the middle of the network, or physically they're in the middle of the network in some way, I should say. But they perform functionality that goes further than simply IP. So in some way they're doing processing on packets which would logically belong at the host on the edge of the network. And I've tried to draw it just on this device here in a router. I don't know how to draw a middle box in our diagram because it doesn't really fit. You can see here I've drawn that it's interfering with this data flow somehow between the sending TCP and the receiving TCP. It's mucking it up. The reason for middle boxes is that people use them to add new kinds of functionality. So a NAT box is one example, and we'll see exactly what a NAT box does just in a short while. There are other middle boxes you might have come across too. A firewall is an example of one, and an intrusion detection system. So to understand more about why we have these middle box devices, let's talk about their advantages and disadvantages. They have some very strong advantages and very strong disadvantages, so they're quite controversial. The advantages really have to do with the deployment of new functionality. Often it's possible to deploy new functionality just by upgrading one box in the network and turning it into a middle box. This is a wonderful alternative compared with, for example, upgrading all of the routers in the network or upgrading all of the hosts, both of which might be well nigh impossible or take a very long time. So if you can deploy something with a middle box, there's a very strong incentive to. If you're in the IT business too, a middle box can also be quite helpful in that if you can deploy it at a good position in the network, it can see traffic from many hosts, and so it provides almost a scalable point of control. It's easier, again, than deploying functionality on many different hosts in the network. You can sort of almost do that by deploying a middle box. On the other hand, it comes with some pretty strong disadvantages. This middle box breaks our layering model. It very much runs counter to it. Now, you could say, well, so what? It was only an abstraction, we'll just break it. Fine. What that does is it interferes with connectivity. This means that connectivity is no longer just a simple matter of sending and receiving IP packets, and often strange things will happen. We will have strange side effects depending on exactly what that does, some of which can complicate the future deployment of things. So and we'll see more about this when we get to NAT boxes. This is the primary downside, that they really make the network more complicated. It also turns out that a middle box is a pretty poor vantage point for implementing some functionality. We simply see packets going through the network. If you wanted to do a lot of functionality like intrusion detection, for instance, you might want to see the web pages or complete documents. But it's difficult to see that at the packet level. You would maybe need to reassemble all of the packets into complete documents to inspect them. That can be a lot of work, and it's not always possible if, for example, end-to-end encryption is used, so that inside the network you can't see the contents. So let's move on now. That's middle boxes. You've heard about this class of devices. Now we'll talk about a NAT box, or a network address translation box. This is a specific kind of middle box whose job is to translate addresses. And it translates addresses to connect an internal network, which has many hosts, to an external network using a very small number of addresses, or a relatively small number of addresses in that network. It's very much motivated by address scarcity. So NAT boxes have been around since IPv6 was proposed and explored. They've sort of really developed concurrently, and they were first proposed as a solution to the address scarcity problem, really as an alternative or a short-term measure before IPv6 would hit. They're really very controversial at first because they of the way they break the layering model and the damage they cause. But over time, they've come to be accepted as part of the internet architecture. Or maybe that's too strong. Maybe I should say they're accepted as a widely deployed networking technology that we just have to live with today. So I still really haven't told you very much about what a NAT box is or how it works. Let's zoom in on a NAT box. And I'll do that just by sketching the common scenario that we're going to talk about. I do want to point out that there are many variations on NAT technology. So if you look it up on the web, you'll potentially see all sorts of different ways that NAT works. The variety I'm going to talk about fits our common home usage scenario. It's actually a network address and port translation. So the scenario is this. You're at home. This is your home here on the left-hand side. You have many computers at home, maybe. I don't know, 5 computers, 10 computers, 2 computers, I don't know. You're connected to the internet via your ISP. Of course, your ISP gives you a single public IP address to connect. It doesn't actually want to give you many more IP addresses, particularly since we're running out. But you want to have as many computers as you like. You set up your computers in your home network, and actually you can give every computer what's called a private IP address. There are reserved prefixes for private addresses. For example, one of them is 192.168.0.0/16 is one. 10.0.0.0/8 is another one. You might see these numbers around quite a lot. They're private addresses, so this means they can be used on anyone's private network. You just can't really attach them to the public network because they don't have any unique meaning. Nonetheless, we can set up our home network and give every computer its own IP address and be perfectly happy. What the NAT box will do is it will translate between these many private addresses at home and the one unique public IP address in the ISP. To the computers at home, it will make it look as though everyone has their own address and they can use this to talk to hosts out on the internet. To the ISP or other hosts out on the internet, it will make it look like there's a single machine at home. I see I've drawn this pink line around all of the boxes. They're sort of looking from the outside as though they're one big happy machine that sits at the public IP address that the ISP has given you, which the NAT box is reusing. So that's the functionality that a NAT box is going to achieve. And just to point out, the NAT box, often a NAT box will be integrated into a wireless router that's part of your access point, and it's often part of a firewall since it's providing some firewall-like technology in any case. So you might not be buying a NAT box, but you might find that NAT is in many of the boxes you use to connect your home network to the internet. So let's dive in a little bit and talk about how NAT works. We've talked about the goals, how it's trying to translate the addresses. How does it do it? It does it by keeping this big table that has a mapping between the internal address for the home side and the external address for the internet side. Now, in the table that I've shown here, the mapping is between an IP address and a port to another IP address and a port. This is sort of typical of the way NAT technology is used inside homes. This is actually technically called address and port translation as opposed to only address translation. The reason you do this is that if you have many computers at home and they're using the internet all at once, well, we can't map them all to the one IP address without getting confused. We would really like an entry in this table to map uniquely from the left side to the right side and vice versa, so we could go back. To do that, we can use port numbers and map a combination of IP address and port number on the left to IP address and port number on the right in a unique way, so that there's a one-to-one mapping and we won't get confused about what belongs one side to what on the other side. This is an example table of a mapping that I just made up. So let me point out a few things about this table. Here we have the IP addresses inside the house. These are private IP addresses. Now they map to another IP address on the external side. That's this one. This is just one public address. So while there were many internal addresses, there's just one public address. So all of the different IPs map to that same one public address. The way we're disambiguating this is using ports. When you made a connection, you also have if it's a TCP connection, a TCP port. So we're going to assume the traffic here is TCP for the moment. The port numbers are shown here. Different hosts might have different port numbers. It turns out that two of these different hosts actually by chance use the same port number. Well, when we map to port numbers on the external side, since we've got the one IP address, well, all the port numbers better be different so we could know which internal thing it maps to. So you can see here that the different combinations are mapped to 3 different port numbers. None of these port numbers can be the same. And none of these port numbers needs to be any of the original port numbers. It can all get redone. I've shown them here as sequential, 1500, 1501, 1502, that's chosen on the output side. But really, it's more likely a NAT box would choose them randomly because it's slightly better for security. Okay, so if that's still a little puzzling, let's just try and work through an example to see what happens. The NAT box has this table. To use this translation table, as packets come and they're going from the internal side to the external side, the NAT box is going to use this table and rewrite the IP header of the packet according to the table. And for packets coming in from the internet to the private side to the internal region, the home network, is also going to rewrite the headers of the IP packets according to this table. So let's see exactly how that would happen. Imagine that you just have this table, that your NAT box is somehow configured with this table. I've just shown one entry in this table. There would normally be many, but this is the only one we need for this example. It maps this internal pair of IP address and port to an external pair. So if we have a packet that's going from this internal source to an external destination, say a big popular web server, I've just used X for the IP address and Y for the port. Let's write down on the internal side what the source address would be of this packet. Well, it's going to be the internal source, and we know here from the table this one is 192.168.1.12. And the port, which I'm showing after a colon, is 5523. I recall that a port number is just a 16-bit number. It's used in TCP. We mentioned that very briefly at the beginning of the course, and we'll see that in more detail when we get on to TCP. What about the destination? Well, where do we want this packet to go to? We want it to go to IP address X and port Y. So the packet will then proceed through the NAT box. As it goes through the NAT box, for an outgoing packet, what we want to do is look up and rewrite the source IP and port. That's right, this box is going to change the IP header, so it's going to rewrite our traffic, which can be very confusing. So the source is going to get changed according to our table. We map this incoming source and port to this particular external IP address and port. So now the source will be 44.25.80.3:1500. Oops, a little squish there. The destination is going to be unchanged because we want it to go to x:y. And it will reach that web server, which will hopefully do some things and send a reply. Moving on, now it's sending the reply. So our packet is coming from the external side to the internal side. Let's look at that packet. On the external side, what do we have? Well, the source here, since it comes from this web server or whatever the external source is, it's going to have IP address X and port Y. The destination, where's it going to go to? It will reply to whatever the source is on the packet it received. And I can remember the source, we made this external IP address and port. So the destination of this packet will be the previous source, which is 44.25.80.3:1500. That packet arrives at the NAT box because the destination IP address takes it there. And then as it goes through the NAT box will look up and rewrite the destination address. It's now going to map that from the external name to the internal name. Okay, so let's go through. On the internal side, the source, well, that's going to be the same. We didn't change that. Will be x:y, meaning it really came from this external web server. The destination will get mapped, according to our table, to 192.168.1.12:5543. And that will be routed to this internal host. And so we've translated between these addresses. There's one other bit we need. You might wonder how this table is formed in the first place. Now, you could maybe have your network administrator fill it in by hand, but that would be cruel and unusual punishment. For any reasonable networking technology, we want to automatically create this mapping table. And we can do this by populating the table whenever a host on the internal side first makes a connection to something on the external side. Suppose you're surfing the web and you contact a particular web server. Then you're going to send this packet from the internal source to the external destination. Now, if the NAT box can recognize this at the beginning of connection packet, the very first TCP packet, which it can, we'll see how later when we get to TCP, but it will look to see if something is a TCP start of connection or SYN packet. If it is, the NAT box will make another entry in the table. It will copy the source, which was here, 192.168.1.12:5523. It will actually take this and copy this into this table. I've actually had already written that in this table. It'll make a new entry. The destination was still x:y. And on the other side, since this is a new entry in the table, it doesn't have an external IP in port yet. It will fill in the external IP because that's the one it has from the ISP. Goodness, I can't remember what it was I had. Let's just say 180. I'm sure, well, whatever it is. And let's say the port that it's going to is, or maybe it's going to port 80. Sorry, that's not where it's going to. This is what we're going to put to the source. So I'm just going to map that. I had 1500 before. The point is this 1500 port, that's chosen at random. This is really going to be the key in this table, the one thing that's unique, since the external IP address will all be the same. So on the outgoing side, we've then moved it to our 44.25.1.80:1500. The destination is still x:y. Don't worry if I've used a slightly different external IP address. It's just meant to be whatever the NetBox is configured with. This one is configuration. But once we've done that, we have populated an entry in the table. Then when a reply comes from that external host, we're set. We'll know how to map it to the internal one, and we can continue using this. Eventually, we'll reclaim the space from this when the connection's closed down or hasn't been used for a long time. So that's how a NatBox works. And just to wrap up, I'd like to talk about some of the pros and cons of NatBoxes. There are definitely some downsides here, and that's why NATs were really very controversial. The connectivity has been broken. We said that breaking the layering abstraction would interfere with the connectivity and cause strange side effects. Well, it has, and hopefully you can realize exactly what one of the side effects is here. That if you want an internal host to communicate with an external one, you can only do it by having the internal host send the incoming packets to the internal host has to make a connection to the external host. You can only send incoming packets, that is from the external host to the incoming one, after this outgoing connection has been set up. Well, that actually fit quite well with web usage in the early days, because your client at home is usually making a connection to a web server. That's exactly what we want, and then the web server can reply. Of course, it doesn't work very well if you want to run a server at home and have people contact you, or if you use peer-to-peer technologies, or apps, including things like Skype. These do not work very well with NAT boxes. Or at least NAT boxes pose a big complication for them. So this is a good example of how NAT boxes have strange side effects, which can make it very complicated for apps to work. There's a lot more to this. I'm not going to go into too much detail, but you need to do a lot to get a NAT box to work well. You might have noticed I'm talking about TCP, so actually NAT doesn't work so well with connectionless kind of transports like UDP. It also breaks apps which somehow expose their IP addresses. The NAT box is translating between internal and IP addresses. If the IP address is in the header, if you use any other mechanism to convey it, like you found out your IP address and put it in a packet and told someone, well, it's not going to be the right IP address by the time it gets to the other side, because the NAT box won't have translated it. And in general, to get something like a TCP connection to work, there's a lot of other traffic that goes with it. As well as a TCP connection, for instance, you might have ICMP traffic that goes with it. You might have DNS traffic on top of UDP. Later we'll see that this is the traffic to map between host names like www.uw.edu and the IP address of their servers. So all of that traffic has to get to and fro through the NAT box properly for the overall application to work. Otherwise it will only half work and will have these strange effects. So these are the downsides. What are the upsides? If there weren't upsides, we wouldn't be using these devices. NAT boxes really have been quite effective at relieving much of the IP address pressure. Many homes use NAT boxes to connect multiple hosts behind NATs to the public internet. So they have really greatly helped with the use of the address space, and they really pushed off the exhaustion of IP4 addresses by a long shot. They're also very easy to deploy. You can deploy it rapidly on your own at home and gain some value from it. This is really, I think, why NAT is rolled out. These incentives are very much in favor of its deployment, since you really have very few alternatives, even though there are downsides. And NATs also provide useful functionality. For instance, as well as all of this helping with addresses, they're also providing some kind of firewalling technology. Maybe a weak one, but one nonetheless, because external hosts can't connect to any of your internal hosts so easily. There will be no state in the NAT box, so it will simply drop a packet because it can't map it properly. It also helps somewhat with privacy, since in the internet, maybe your 7 machines look like one machine. So you can't really be sure who behind a NAT box in a department was necessarily doing what. And I think over time, NAT boxes are part of the internet now, at least they're widely deployed. They're something we need to live with. So many of the kinks will get further worked out as NAT boxes get cleaned up a little bit over time. Technologies such as NAT traversal, you might have heard of, for instance, will streamline how applications from the public internet can get through NAT boxes to devices on the other side. Applications like Skype use NAT traversal to operate more smoothly behind NATs. And a lot of this functionality has been sorted out. So there you have it. Now you know about NAT boxes and how they work.